Thank you so much for the introduction, and thank you all for coming here today. Again, my name is Debbie Senesky. I'm an assistant professor in the Aeronautics and Astronautics department. I'm going to talk a little bit about my research, but before I do that, I'm going to tell you why it's an exciting time to be an aerospace engineer. But we have to go back 100 years to really grasp and understand where we are today with aerospace engineering. So this is an image of the experiments of the Wright brothers in the early 1900s, so over 100 years ago. They conducted various failed experiments in order to achieve human flight, in order to allow us to traverse the sky. They were able to use and compile mechanical structures as well as propulsion systems to allow us to fly in a controllable and sustainable fashion. 70 years later, this work really inspired us to eventually do the same thing with rockets and place a man on the moon. So today, Elon Musk and Gwendolyn Shotwell are working together with their engineers at SpaceX to try to get to Mars. So Gwendolyn Shotwell was here on Wednesday talking about their work with the Falcon 9 rocket and also their experience with many, many failed rocket landings. So this image on the left-hand side here is showing their experimentation that didn't work out. But what was mentioned in Gwendolyn's talk is that it actually hit the target. Although millions of dollars, unfortunately, were lost in this experiment, they were able to launch and hit the target. Moving forward, years later, now the Falcon 9 rocket can actually land on the target. How many of you have seen this video recently? If you have not seen this video, please watch it. It really is quite inspiring. And so the goal here is to be able to reuse rockets so that we can eventually go to Mars and maybe even come back. Or perhaps we have space tourism as well, right, where we would travel around the moon. And so this is the spirit of aerospace engineering right now, really doing the impossible. Many of the students, undergraduate students and graduate students here are really interested in this area, and our department recently started an undergraduate program 2 years ago. So we haven't officially graduated any aerospace undergraduates here at Stanford, but stay tuned. In a couple of years, we will have graduates in our program. So why space exploration? So we're really interested in understanding our solar system. We want to know big questions. Are we alone? Is there another planet that we could live on and have a new type of habitat? Are there resources that we can harness and bring to Earth for our benefit and for our sustainability? But in order to do all of those types of exploration, we need to conduct experiments and missions on various types of terrains, very extreme environments that are radiation rich. They also have extreme temperature cycles from very, very cold cryogenic temperatures all the way to extremely hot temperatures. Also, our various planets and bodies in our solar systems have different terrain that we have to navigate. So my research is focused on developing technology for extreme harsh environments. Our current focus in particular is in the Venus environment. So Venus is our neighboring planet. There's an image on the left-hand side of Venus. And Venus is actually very much like Earth. It actually has the same mass and the same diameter. So it's very much like Earth with respect to its density. But it's also very, very different from Earth. Number one, it doesn't have a magnetic field. Number two, it doesn't have a moon. Also, it doesn't have tectonic plates like Earth. More importantly, it also has an extremely harsh environment. The surface temperature of Venus is around 480 degrees Celsius. Also, it's chemically corrosive. It has supercritical CO2 in its ambient, as well as sulfuric rain clouds. So this is an image from the first color image of the Venus surface, taken in 1982 by the Soviets. Again, many failed missions were conducted before this. The U.S. has yet to send a lander to Venus. However, there are many proposed missions and various design concepts to do that in the near future. So, what are some of the challenges with exploring a place like Venus, our neighboring planet? So what would happen if you were to put your cell phone on the Venus climate? If you were to land on Venus, what would happen to your cell phone? It would melt. It would bake. Anybody have issues putting your cell phone on your dashboard of your car in the sun? Right? So heat actually can degrade electronics. What happens is your semiconductor material starts to generate a lot of electrons due to the thermal energy, and your electronics don't work the same anymore. They work in a very unreliable fashion. So this is a chart of various semiconductor materials that can help us extend the operation points beyond silicon. Okay, so silicon, we're in Silicon Valley. It's a wonderful material. NASA and other aerospace researchers do use silicon. However, they have to actively cool it and shield it from the space environment. And that adds to payload. And every pound that you put in space costs $10,000. So until we actively have these reusable rockets, we really need to think about very carefully what we put in space. And every gram of material really has to function. And so there are alternative materials that my group has been working on, in particular wide bandgap semiconductor materials. You could think of them as ceramic materials. So many of you may know ceramic materials that are reinforced, that are used to reinforce metals, such as diamond, for example. Diamond is a very hard material. But a lot of the challenges with many semiconductor materials is that they don't transport electrons. Right? They're great thermally and mechanically, but it's very difficult to make something like a transistor or a sensor device out of these materials. So my group has been working with gallium nitride in particular. What's attractive about gallium nitride is that it has a very high melting point, 2,500 degrees Celsius. So thermally, it's very stable. It takes a lot of energy to break apart the gallium and nitrogen bond. In addition, it has a very high energy band gap. It takes a lot of energy for electrons to jump the valence band, thermal electrons, and so therefore it can work up to 1,000 degrees C before thermal runaway starts to dictate the electron transport in your electronics. Also, due to the band gap, it's actually sensitive to the ultraviolet regime, which is very advantageous in optical imaging in space. So gallium nitride is an emerging semiconductor material. It is heavily used in the power electronics area because it can handle very high voltages and also function at very high frequencies. In addition, this material has been used to develop the blue LED, so Nobel Prize winning work for gallium nitride to create the blue LED. Other disciplines include sensing, solar cells. The highest efficiency solar cell actually has a layer of gallium nitride within it because it can capture a portion of the ultraviolet spectrum. In addition, micromechanical structures such as RF resonators and also nanostructures are being developed in this platform. So gallium nitride is a little bit different in comparison to silicon. So I just want to take some time to explain its transduction. So with silicon, in order to make a transistor, you have to dope the material. You bombard the material with either boron or phosphorus in order to make it more conductive. Gallium nitride is a little bit different because it leverages a quantum effect. So this is an image of the atomic arrangement of gallium nitride. If you start to sandwich composite variants of gallium nitride together, in particular aluminum gallium nitride and gallium nitride, what happens is you actually form a nanodimensional sheet of electrons, and it's called the two-dimensional electron gas. And so this is how the electrons flow through the material. It's through the generation of this composite material that forms a quantum well, a high density of electrons. The sheet of electrons, you can think of it as just a 1D sheet of electrons flowing through this composite material, and then we can modulate it through the implementation of a source, gate, or drain, just as you would with your silicon-based transistor. So it's a slightly different technology. So we have adapted the gallium nitride platform to create high-temperature electronics. So this is a cross-section of the electronic structure. We use silicon wafers. We do a lot of work to develop the buffer structure to be able to grow the device layer gallium nitride films. We also have shown that atomic layer deposited dielectrics actually help them work better at elevated temperatures. So unfortunately, it's a little bit hard to see, but this is a picture of a glowing chuck at 600 degrees Celsius. And we have our gallium nitride chip on top of the chuck, and we're probing it, and we're actually able to get electronic signals. So these are IV characteristics going from room temperature all the way to 600 degrees Celsius. So this is a transistor with controllable electrons flowing through that two-dimensional electron gas at 600 degrees C. So this tells us that we can actually make high-temperature electronics for places like Venus. And we're also able to suppress a lot of the leakage in these types of devices through the introduction of nanomaterials. So my group is working to adapt this new semiconductor material platform to create multifunctional gallium nitride nanoelectronics. So in addition to a transistor, you can also think about designing sensor technology, resonator technology, energy harvesters, all on the same chip. So we can use the same material to create a multitude of devices. So these devices can then sense the external environment, they can also power themselves, and they can also communicate data. You could think of this as something like a ChipSat, right? You have multifunctional behavior of your electronic elements, however, they are fabricated all together on the same chip. So this is an example of a device that my student has developed. This is a gallium nitride pressure sensor. You can see here this chip on the right-hand side is 1 centimeter by 1 centimeter in size, and it actually houses about 40 prototypes of her sensors. So these are very, very small devices that can really do many, many things. What we do in order to test these devices is we use a small pressure chamber that can apply high pressures and temperatures at the same time, and then we're able to characterize the electronic signals of this type of device. So these are some of her results showing room temperature all the way to 300 degrees C. Again, you have IV characteristics. You have this resistance response and then saturation. So what that means is it's functioning like a transistor. It's able to switch. In addition, you have pressure sensitivity. So the device I've shown you here is an adapted device that actually you remove the substrate and you have a pressure-sensitive diaphragm. So as you apply pressure, it actually displaces the diaphragm and allows strain to be induced in your transistors. And as you increase the pressure, you get a shift in the IV response. And so you can use this to convert pressure signals to electrical signals that you can then process using your onboard electronics. So we've been collaborating with NASA to study these materials in harsh environments. In particular, we've been using the Venus chamber at NASA Glenn Research Center. This is a chamber that simulates the Venus conditions. It has all of the chemistry that you would find on Venus. Also, it has the pressure, 90 bar of pressure, and elevated temperature, 480 degrees Celsius. So I don't want to have this type of instrumentation in my lab. So I'm glad that NASA has this type of facility. So my students go to NASA every summer, and these are samples here of various ceramic semiconductor materials that we've inserted into the Venus chamber. And we're studying the weathering of these materials to really understand the evolution of the material due to the caustic Venus environment. In addition, we've been working with a startup company to look at nanocoatings that might help with its weather resistance. So as I mentioned before, Venus has a sulfuric ambient. It actually has sulfuric rain. So that can really degrade electronics. So what if we had a nano coating that actually repelled that sulfuric rain and prevented it from actually etching and eroding the surface? So what you're seeing here is a droplet of sulfuric acid. Yes, my students have a lot of fun in the lab, and we worked very carefully with the various chemistries that we utilized. This is the nano coating, and you can see this sulfuric acid is balling up on the surface. It's not wetting the surface, it's actually repelling the surface. And so that can help with allowing electronics and other materials that would be used in a Venus lander to actually resist the sulfuric rain found on Venus. So this is a new area that we're looking at, and we are actively pursuing a deeper understanding of how these materials actually repel the Venus environment. So another mission that is emerging in the field of aerospace is being able to go to deep space using ChipSats, so actually exploring beyond our own solar system. And so in order to do that, it would be very, very difficult to conduct with your traditional spacecraft. You would need a lot of energy and propulsion to get to somewhere like Alpha Centauri, which is our nearest solar system. So what is proposed is that you have a variety of ChipSats that would be able to sense, communicate, and power themselves beyond our solar system. And so these constellation of ChipSats would then communicate with each other, collect information, and send it back to Earth. But how do we get there? So one of the concepts is to use laser-based propulsion on Earth to launch ChipSats that are propelled with a light sail. So you can use radiation pressure on a very thin membrane in order to propel these ChipSats over to Alpha Centauri. So this is called the Starshot Breakthrough Initiative. It's being funded by Stephen Hawking and Yuri Milner, and they are looking to really send a ChipSat to Alpha Centauri. It would take 20 years to get there, and would be really interesting to understand more information outside of our solar system. But in order to develop these ChipSats, you need to have technology that would be resilient over that entire journey. Again, there's going to be thermal cycling and also radiation attack. So depending on where you are in the space environment, whether in low Earth orbit, Venus, or deep space, there's going to be a variety of temperature swings and also a variety of radiation levels. And this is just shown here graphically. And so radiation is composed of high energetic particles such as protons, electrons, or neutrons. And when they bombard your materials, they actually degrade your materials. And when they bombard electronics, it could actually degrade your signal. And so what we do now is heavily shield the electronics in order to allow them to perform in these radiation-rich environments. So my group has been developing another platform for high temperature and radiation-rich environments. We've been using graphene, which is a sheet of carbon atoms. It's an atomic layer thick sheet. So you can think of the carbons in a chicken wire formation. It actually has amazing mechanical properties. It's stronger than steel. Also, it has interesting electronic properties as well. It is a transparent material, and so it allows all of the optical spectrum to be transmitted. And so we've been using this as a conductive layer to develop ultraviolet photodetectors. So what we do is we transfer the graphene to our gallium nitride substrate. We do patterning, and then we create these interdigitated electrodes, which are conductive. And when we shine ultraviolet light onto this structure, what happens is we generate a current. And that current is proportional to the intensity of the ultraviolet light. And so we can use this as an ultraviolet detector. This is an image of our graphene on gallium nitride device. So the black fingers there are around 10 microns in width. You wouldn't be able to see this graphene with your own eye. We actually have to use a scanning electron microscope in order to resolve the graphene and actually know that it was printed there on the substrate. So we have tested this device under ultraviolet conditions, and also we've irradiated it with protons at various fluences. So the black curve is the IV response under dark conditions, and then the colored curves are the IV response or current voltage response under ultraviolet stimulation. And we observe the evolution of the IV characteristics upon irradiation of protons. And we can see that those IV curves start to collapse. So the radiation is actually not degrading our device, and this is an unshielded electronic device that's surviving high proton irradiation. So we've studied the responsivity of our device over increasing fluence, so over protons per area. We can see as that increases up to around 2.5, 10 to the 13 protons per centimeter square. It's very, very stable in comparison to your traditional metal electrodes. We've also studied the response of the graphene layer using Raman spectroscopy. Raman spectroscopy is a materials characterization technique. It actually allows us to get the fingerprint of the material. We can identify the type of material and also the crystallinity of the material. So what you're seeing here is the graphene before the proton irradiation and after proton irradiation. And you can see we're getting sharp peaks. So this 2D peak is a very high intensity peak, and that tells us that the graphene is of very good quality. And after radiation, we see minimal degradation in that peak. And so that's telling us that even after an intense irradiation, this nanomaterial is able to survive. So we've adapted this sensor to create instrumentation for a CubeSat. So we have our individual ultraviolet photodetectors. We've placed them in an array, and we've also placed an optical aperture on top of that array. So as the sun is shining on this sensor, it's illuminating one of the sensors, and we can monitor the intensity and then back calculate the location of the sun. So we've implemented this miniature sun sensor on a CubeSat through the QB50 program. It's a constellation of 50 CubeSats at various universities around the world, and Stanford has a CubeSat, the Discovery CubeSat. And so you can see an image of it here, the solar panels, and our gallium nitride graphene sun sensor, optical sensor. And so we're waiting for this CubeSat to be launched so we can evaluate and validate the performance of our sensor. Finally, we're implementing our sensors on a suborbital launch as well. And this is a great training opportunity for students because they get to engineer under time constraints. They also get to engineer under size constraints and power constraints. They really have to be innovative in order to implement their devices on things like CubeSats, because again, there's a lot of space constraints in particular. So this is an image of our sensor payload. We have some interface electronics. We also have our gallium nitride sensor, and we're gearing up to implement it on the Wayfinder CubeSat, which is developed by Boreal Space, which is a company based out of NASA Ames. We're also working with interorbital systems to launch this CubeSat in suborbital flight, and we're going to measure the magnetic field signatures of the Earth during that suborbital flight. So hopefully I've given you a sense of the development of electronics for harsh environments. So in addition to space exploration, there are also ground-based applications where this work can benefit, such as oil and gas exploration, monitoring of combustion engines, and also geothermal well bores as well, which also have extremely high temperatures, and it's very, very difficult for electronics to perform and survive. So with that, I'd like to acknowledge the students in my group who have conducted a lot of this work, and also the funding sources as well. And I'm happy to take any questions.